N-topologies. Basically, the idea of a universe endowed with more than one topology is not new. The notion of b-topological space was introduced by Cully in 1963, and it seems that that this line of research went at least in two or even three directions. The first one is based on the idea of generalization. So generalizations of b-topology were studied, for example, by Banerjee and Pal. They've examined so-called generalized b-topologies based on Chasser's idea of families closed under arbitrary unions. Boonpok investigated B-minimal spaces. As we remember, minimal space or minimal structure is the one characterized by the fact that at least empty set and the whole space belong to this family. Pui Wong, Viriapong, and Kampakdi analyzed B-weak structures. And as we know, weak structure is the family such that at least empty set belongs to this family. Well, the second direction is to transfer the notion of b-topological space into, well, alternative universe. So, for example, we had b-intuitionistic topological spaces, yes, based on the very idea of intuitionistic sets and intuitionistic topologies of Tucker. And the third direction is this one, just to increase the number of topologies on our space X. So nowadays some authors investigate 3, quad, and even pentatopologies with 5 topologies. Alan Kahn studied the possibility of n-topological spaces, which may be considered as the generalization of the idea of Kelly. Look to the bibliography. And also one may recall the idea of binary and n-ary spaces of Jyoti, Tangavelu, Sitalakshmi, and Kamaraj. Among all these concepts, there is one which seems to be very elegant. We think about N-topologies introduced by Lellis Thivagar in 2016. And this presentation is based almost entirely on the initial paper of Thivagar, so all credits go to him, to Professor Thivagar. All the credits. Assume that X is a non-empty universe and tau 1, tau 2, and so on, tau n are n arbitrary topologies defined on X. We define the following collection named n tau. We take A1, A2, and so on, and An, which such that A1 is the first topology, A2 is the second topology, and so on. We form their union, and then we form the union of this union with the intersection of some open sets, such that B1 is opened in the first topology, B2 in the second topology, and so on. Well, in particular, if n is equal to 2, then we obtain sets of the form A1 plus A2, where A1 is from the first topology and A2 is open in the second topology, plus the intersection of B1 and B2, where B1 is open in tau 1, B2 is open in tau 2. Well, one can prove that this collection satisfies the following axioms. The whole universe and the empty set are open. There's a closure under arbitrary unions and under finite intersections. So the statement above, this list of properties, allows us to call the pair X and tau an n-topological space on X. And the elements of n tau are named n tau open sets, and their complements are n tau closed sets. This is clear. For example, let n be 2x and x, and our universe X consists of 4 elements A, B, C, D. Here we have the list of sets which are open in topology tau 1, and here are all these sets which are open in tau 2. You may easily calculate the sets of closed sets of closed sets, yes, and then you are able to compute this 2 tau O of x, so the set of elements which are open in 2 tau topology in this case, and the set of the elements which are closed in our 2 tau topology based on tau 1 and tau 2. Another example, here we have 3 topologies and their classes of open sets are respectively tau 1OX, tau 2OX, and tau 3OX. And then you may calculate tau 1C of x, so closed sets, and the same for tau 2 and tau 3, and finally you obtain 3 tau OX. So this is N topology for n equal to 3, and this universe and this topology is tau 1, tau 2, tau 3. And here is the class of closed sets in this 3 tau topology. You may treat these calculations as an exercise. They are simple because our universe is finite. Well, some general properties. So for example, if we have 2 n-topologies on X, then their intersection is again n-topology. But the union of 2 n-topologies on X may not be n-topology. Counterexample, if we have universe ABCD again, and we have these 6 topologies on X, then assume that our 3 tau 1, our first 3 tau topology, is based on tau 1, tau 2, tau 3, while the second 3 topology on X is based on tau 4, tau 5, and tau 6. And then one can calculate this union. Well, first you have to calculate 3 tau 1 and 3 tau 2, and then you may calculate their union. It will be like this. This example is also taken from Thivagar. And this is not 3 tau topology because, well, consider these two singletons, A, B. They both belong to this union, but their union does not belong to 3 tau 1 plus 3 tau 2. We define n tau interior of S contained in our universe in a standard manner as the union of all open sets contained in S, and analogously n tau closure of S is the intersection of all n tau closed sets in which S is contained. So these definitions are modeled after typical topological space, of course. In general, the very basic properties of interior and closure are standard. Now, for example, if A is contained in B, then n-tau closure of A is contained in n-tau closure of B. N-tau closure of A plus B is equal to the union of n-tau closures, and n-tau closure of intersection is contained in the intersection of n-tau closures. So these are expected properties. Moreover, one can prove that, well, it should be small x here, and that it belongs, that our point x, small x, belongs to n-tau closure of A, even only if the intersection of G and A is not empty for every n-tau open set G containing X. There's also a notion of subspace topology. Okay, it is also typical. Also, the notion of continuity has been defined in this environment, and this notion is standard. Okay, function is continuous if the inverse image of every n-tau open set in Y is an n-tau open set in X. But here you have an example of such situation. Yes, you have two universes, namely X and Y. They are finite. You have topologies on these universes, tau 1OX, tau 2OX, tau 1OY, and tau 2OY. Well, maybe it would be better to replace tau here for me, for example, with other letter, yes, like gamma or mi. But be as it may, everything is okay. Yes, you have two universes, two topologies on each universe. Here you have two tau OX topology and two tau OY topology, according to the idea of Thivagar. And you can check that the following function is two continuous, two star continuous. Yes. Well, that's all for today. Here is the bibliography. You can check these papers. You can easily find them in internet, and you can also find articles by all these authors which have been mentioned in introduction. Thank you very much for your attention.